Hello, my name is Professor Van Cholitowski, and I will be transferring to you the knowledge necessary to become a good electronic engineer in the specific area of analog electronics. I will be preparing for you the following groups of courses: basic electronics, including materials and devices, electronic amplifiers, noise in electronic circuits, electronic filters, electronic testing and diagnosis. Then, power electronics, including DC to DC converters, DC to AC inverters, AC to DC rectifiers, photovoltaic systems. Finally, electronic simulation and optimization, including electronic circuit simulation and electronic optimization. Electronics is considered a branch of physics, which means that for following these courses, you need to have basic knowledge of physics. Terms as velocity, force, power, momentum, energy, and especially terms describing electrical quantities, voltage, current, electric charge, electric power, are ones you have to be familiar with. Physics comes together with mathematics. Basic knowledge of trigonometry and other transcendental functions is a must. In some cases, solving of ordinary linear differential equations will be needed. Specific to the electronic engineering are complex numbers and the related algebra. Here, especially rational functions of polynomials of complex variable with real coefficients are encountered frequently. These are produced by application of the Laplace transform to the differential equations describing the circuits. Methods for circuit analysis are needed to be known in order to extract the performance of devices, circuits, and electronic systems. You will need to use the Kirchhoff's current law most frequently, since the electronic devices are modeled by current equations, current sources. That means the nodal circuit analysis is preferred. Basic knowledge of formal circuit theory, such as four-terminal representation of a circuit, will be necessary too. It looks complicated, but I believe you are already familiar with most, if not all, of these, and you will proceed swiftly. To start with, we will explain some basic physical principles related to the mechanism of conducting electric current in semiconductors. The planetary model of the atom proposed by Rutherford in 1911, based on the classical principles of Newton's mechanics, assumes that an atom consists of a nucleus, which contains protons and neutrons, and electrons orbiting the nucleus. The electric charge of an electron and its mass are given to the right. Now, a proton is a carrier of the same charge as the electron, only it is positive. The mass of the proton is 1,845 times greater than the mass of electron. The third particle is a neutron that is electrically negative. The electron energy is often measured in electron volts. 1 electron volt corresponds to an energy as given on the right. It is the energy that an electron obtains by crossing the path between 2 points with a potential difference of 1 volt. The term energy state of an electron, or abbreviated state of electron, means the energy of an electron. The set of all states of electrons in an atom is called the state of the atom. In 1913, Bohr laid down the basic laws that changed the notion of the atomic model. According to this theory, an electron cannot possess arbitrary value of energy, but only certain discrete energy states. When it is in a state that corresponds to one of these discrete levels, the electron does not emit energy. Energy, they vary from material to material, but are all characterized by the fact that the angular momentum of the electron must be an integer times of h divided by 2 pi, where h is the Planck constant as given below. In other words, if Mn is the mass of the electron, v is its velocity, and r is the radius of the orbit, the angular momentum of the electron moving in the nth orbit is given below. During the transition from a higher to a lower steady state or orbit, the electron emits energy in the form of radiation whose wavelength is given as lambda, where E2 is the initial energy, E1 energy corresponding to the new state, and c the speed of light in vacuum. Its frequency is given on the bottom. It's theoretically possible to calculate the energy state of the electron of an atom of a particular element. The figure shows the possible energy levels of electrons in a mercury vapor atom, starting from the level corresponding to the normal energy of the unexcited atom to the energy corresponding to ionization. Some of the possible wavelengths of radiation are also given. Other stationary states are called excited or critical levels. In order to possess these states, the electron needs to increase its energy. The change in energy levels is a consequence of excitation of atoms. If one electron within an atom increases its energy, it moves away from the nucleus at the same time. When this energy becomes sufficient for it to move away so far that the nucleus no longer affects it, it becomes a free electron. This phenomenon is called ionization, and the energy required for this process is called ionization energy. For mercury, it is 10.39 electron volts. Atomic excitation can be performed in several ways. One possible way is excitation by collision with an external electron moving towards the atom. Of interest is the so-called inelastic collision, which occurs when the electron exciting the atom has energy so large that when it collides with an electron from an atom, it can transfer that electron to a higher energy state. In this case, the atom absorbs part of the energy of the outer electron. After an inelastic collision, the outer electron changes the direction of its path and its velocity is reduced. Another possible way of excitation of atom is by the collision of atoms and photons. The term photon means the amount of radiation energy that is equal to the product of the constant h and the frequency of radiation ni in Greek. In this case, the energy of the photon will be absorbed only if its energy is equal to the energy difference between the two possible states of the electron. The photon can either be totally absorbed or will not be absorbed at all. Other ways of excitation will be discussed later. In this figure, it can be seen that the energies are needed to bring the electron of mercury atom to the higher state. In the new excited state, the electron remains very shortly. This time is called the lifetime and ranges from 0.1 microsecond to 0.1 nanosecond. Then the electron returns to its original energy state, emitting electromagnetic energy in the form of a photon equal to the energy difference between these two levels. There are energy levels in which the lifetime is significantly higher and ranges from 10 milliseconds to zero point 0.1 millisecond. They are called metastable levels and shown in green. The relative longer retention time of electrons in these states allows ionization to take place by means of two collisions of atoms with external electrons or photons. Quantum mechanics assumes a more complicated atomic structure than Bohr's model of atoms. Thus, the state of an electron is described by the four quantum numbers n, l, m, e, and ms. The basic quantum number n characterizes the orbit of the electron, i.e., the possible energy of the electron in the corresponding orbit. Its value can be n equals 1, 2, 3, and so on. The quantum number of angular orbital moment L characterizes the shape of and the position of the orbit. Its value is limited by the basic quantum number and can be L equals 0, 1, 2 until n minus 1. It is said that the angular quantum number defines the suborbit. The orbital magnetic quantum number describes the orientation of the orbit relative to the applied magnetic field. Its possible values are m e are 0, plus minus 1, plus minus 2, until plus minus L. The spin quantum number characterizes the orientation of the spin axis of the electron in relation to the magnetic field. Its possible values are plus minus 0.5. According to Pauli's principle of exclusivity, in one system there are no two electrons with the same set of quantum numbers. A set of all four quantum numbers defines the quantum state. In one system there are no two electrons with identical quantum states. Often, the quantum number of the angular orbital momentum is also marked with letters. Thus, L equals 0.1345 and 6 correspond to the letters S, P, D, F, G, H, and I, respectively. In order to denote the state of the excited atom, the basic quantum number n and the azimuthal quantum number are used, so an abbreviated notation is formed. Thus, for example, an atom with one shell and two electrons in it is denoted by 1s squared. For the atom with which the second shell is also filled, the notation is 1s squared, 2s squared, and 2p6. There are 6 atoms in the subshell. The top table below contains the electron configuration of carbon, silicon, and germanium as important materials. An atomic system is a set of atoms that act on each other. This set is arranged in such a way that the atoms are spatially distributed in the forks of regular geometric bodies called crystals. Atoms in a crystal are located several angstroms apart so that they affect each other, which results in a modification of the energy structure of atoms. If two atoms are far enough apart that they do not affect each other, then they form two independent systems. Electrons with the same quantum numbers can exist in these two systems. As these atoms get closer, they affect each other. The distance at which the interaction occurs is an order of magnitude larger than the dimensions of the atoms in the crystal lattice. Two atoms acting on each other are no longer independent systems. Now they form a single system. According to Pauli's principle of exclusivity, electrons with the same quantum state can no longer exist. In this system, there is a shift in the energy levels of electrons. Thus, instead of one energy level, which was the same for both electrons when they belong to the two systems, now two energy levels appear that are very close to each other. If third atom is included in the system, each energy level will split into three new levels. In a solid body, the density of atoms can be of the order of 10 to power 23 atoms per cubic meter. This means that 29, sorry. This means that each energy level has split to countless new energy levels. The system now consists of sets of energy levels grouped around a single energy level that corresponds to an electron in a lone atom. In each set of levels, the individual energy levels are very close to each other. This phenomenon can be more easily interpreted on the assumption that the energy set forms a continuous energy band of possible energies. This band is located in the vicinity of the energy level of an isolated atom. There are as many of these bands as there were original individual energy levels of isolated atoms. The electrons of the atomic system can possess energy within these bands. The bands are separated from each other by energy gaps. States that correspond to the energy gap cannot be possessed by any electron. That is why energy gaps are often called forbidden bands or forbidden zones. This means that if an electron would go from state S to state P, it would need to increase its energy by an amount equal or larger of the energy gap. For semiconductors, here silicon, of interest are distances smaller than d1 on the figure. In fact, dO is the one. The common energy band splits again into two new bands, but on a different way. There are no more S and P electrons. Each of these two bands has 4 n possible states in a silicon crystal at absolute zero temperature. All 4 n electrons will be in the lower band called the valence band. The upper conductive band is empty. The new situation persists with the further approach of the atoms. If the temperature of the silicon crystal increases, an electron can be excited. Thus, it is possible for an electron to move from the valence band to the conductive band. The energy gap, e.g., determines the average number of electrons that can pass from the valence to the conduction band at a given temperature. Thus, it is of fundamental importance for the conductivity properties of the material. It is different for different materials, of course. The top figure on the right shows three typical structures of energy bands in three different crystals. In the leftmost, the distance between the atoms is small. In the next, it is large, B, and in the last, it is between these two, C. The energy gap on the left side is significant above 3 electron volts. For example, for a diamond, it is 6 electron volts. Even at high temperatures, near the melting point, these materials have very few electrons in the conduction band. These materials are called insulators. The part of the figure denoted B, there is no energy gap. The valence and the conduction band overlap. Most metals are characterized by this structure of energy bands. All electrons from the last shell can participate in the mechanism of conducting electrical current. These materials are called conductors. Materials with small energy gap, less than 3 electron volts, are called semiconductor. At room temperature, there are electrons in the conduction band, so they are available to conduct electricity. Their number is relatively small, and therefore these materials are called semiconductors. Semiconductors can be pure elements such as germanium, or the most widely used element in electronics today, silicon, but some compounds perform as semiconductors too. 3,5 compounds, which means that there are elements of the third and the fifth group of the periodic table, gallium arsenide, gallium antimonide, gallium phosphide, and so on, or 2,6 compounds, where there are elements from the second and the sixth group of the periodic table, cadmium telluride or uh, zinc selenide, and so on, can behave as semiconductor. Finally, more recently, more complex compounds such as aluminum gallium arsenide or cadmium zinc sulfide are the like have been used and the like have been used. In the last formulas, uh, x is between 0 and 1 denotes which part belongs to a given material. By changing the value of x, the properties of the material are controlled, and above all, the energy gap. In order to make it easier to cope with, this table gives an excerpt from the periodic table of elements that are important from the semiconductor point of view. This table contains the properties of most frequently used semiconductors. The stated values of the energy gap apply to room temperature only. Namely, the size of the energy gap is a function of temperature. The reason for this is the dilatation of the material, which in fact means that as the temperature increases, the distance between atoms increases. The greater the distance between atoms, the smaller the energy gap. The formula, the approximate formula, is given below. It means that for T equals 0, the absolute 0, the value of the energy gap of the silicon is 1.21 electron volts. At first glance, the change in the size of the energy gap from 121 at 0 to 1.1 at 300 Kelvin is not significant, less than 10%. This change, however, significantly affects the change in the electrical properties of the material. Therefore, the temperature has important influence to the electronic components and equipment. We will now go after the conduction of electrical current in semiconductors. To start with, we will consider a pure semiconductor, silicon, without chemical impurities and with a perfect crystal structure. As stated earlier, the last shell has 8 possible states, of which only 4 are filled with electrons. At the temperature of absolute 0, all electrons are in the valence bond. The conduction band is empty. Each silicon atom is connected to 4 adjacent atoms in the crystal lattice via its 4 electrons in the last shell. In this way, every 2 adjacent atoms have 2 common electrons. Each atom of silicon now has 8 electrons in the last shell. In complex semiconductors, such as gallium arsenide, however, the situation is slightly different, but we have not enough time to consider these details. Let us now consider the possibility that there are free charge carriers in the semiconductor. At very low temperature, this material should be expected to act as an insulator since there are no sources that would produce the energy required for ionization of the electrons in the last shell. This energy can be delivered by a photon coming from or by thermal mechanical vibration or the atom in the crystal lattice. The quantum energy obtained by the vibration of the crystal lattice, by analogy with electromagnetic waves, is called a phonon and represents a measure of temperature. The mean value of the thermal energy that can be delivered to an electron is the order of kT, where K is the Boltzmann constant, given below. At room temperature, 300 Kelvin, this energy is only 0.026 electron volts or 26 milli electron volts, which is significantly less than the energy gap of silicon. This does not mean, however, that all the electrons in the last shell have this energy. The energy distribution of an electron is a statistical quantity, so that there is a small probability that it will accumulate energy greater than the energy gap to become excited. However, even though the probability is small, having in mind the number of electrons in the valence bond, about 2 to power 23 in cubic centimeter, we can conclude that the number of excited electrons will be not negligible even at room temperature, and that it will rise with the temperature. The process of formation of free electrons in a semiconductor is called generation. The rate of generation, G, is expressed by the number of new electrons per unit volume per unit time. The number of free electrons in a unit volume is called the concentration and is denoted by N. It is important to note that the rate of generation, when there are no external causes, is a function only of temperature and not of concentration. When an electron breaks a covalent bond and leaves an atom, one unfilled covalent bond remains in the atom. It can move through the crystal in the following way. Look to the right to the picture. An unfilled covalent bond is filled by taking one of the valence free electrons of some of the adjacent atoms. Now, in a new place in the crystal, an incomplete covalent bond is formed. The process continues and is equivalent to the movement of incomplete covalent bonds through the crystal. Such an unfilled covalent bond is called hole. The motion of the hole is in essence the motion of several electrons. However, as the atom in which the covalent bond is broken has remained positively charged, the whole process can be presented as the movement of possible positive charge through the crystal. Therefore, the hole is also a free carrier of electricity and participates in the process of conducting electricity under the influence on external electric field. The charge of the hole is positive and in absolute value equal to the charge of electron. A certain mass is attributed to the hole, which is close to the mass of electron but different, larger from it. The process of creating new electrons is accompanied by the process of creating holes. This is illustrated below on the semiconductor energy diagram. In the diagram, the lower limit of the conduction band is denoted by EC, and the upper limit of the valence band is denoted by EV. In a pure semiconductor, the number of free electrons is equal to the number of holes, because each electron breaking the covalent bond and becoming free leaves a hole behind. If the number of free electrons in an unit of volume electron concentration is denoted by N, the number of the concentration of hole by P, then Ni equals to Pi, where the index I means intrinsic is used to denote the pure semiconductor. Since the number of available carriers in a semiconductor is determined by the temperature, it is not suitable for use. It is desirable that the number of carriers to be determined by the needs of the user, and it should be independent of temperature. In order for a semiconductor to satisfy these requirements, one type of free charge carriers should be significantly more numerous than the other. This is achieved by the controlled addition of other elements to the semiconductor. The process is called doping, and the element that is added is called dopant. The dopant is also called an impurity. The amount of dopant is very small compared to the basic semiconductor. The typical ratio of the number of silicon atoms to the number of impurity atoms is 1 million. Due to the relationship in it is understandable due to this relationship, it is understandable that each impurity atom is surrounded by a very large number of silicon atoms. So it is very distant from other atoms of the same type. The chemical impurities added to silicon and germanium belong to the group 3 or group 5 of the periodic table, for example, boron and phosphorus, respectively. In the case of complex 3,5 materials, dopants are from the second or the sixth group, respectively, for example, cadmium and tellurium. Let the silicon crystal contains atoms of phosphorus. It has 5 valence electrons in the last shell. The 4 electrons bind covalently to silicon atoms. The 5th electron has no atom to which it would bind. With very little thermal excitation, this electron becomes free. However, no hole was formed during this process. It is true that the phosphorus atom is positively charged, but since it is covalently bound to the 4 electrons in the crystal lattice, it is immobile and positive. The figure on the right illustrates a silicon crystal with a phosphorus atom in the lattice, which resulted in a formation of a free electron and a positive ion. Impurities with 5 valence electrons are called donors because they hand over 1 free electron to a semiconductor. The slides shows the energy diagram of a semiconductor with a pentavalent chemical impurity. Donor atoms introduce an additional energy level. More precisely, this should, in line with previous presentation, be a band. However, due to the low impurity concentration, the donor atoms are largely separated from each other, and there is little mutual influence between them. Therefore, it can be said that with sufficient accuracy that this is an additional level, not band. The energy level introduced by the donor atoms is quite close to the conduction band, about 0.03 to 0.07 electron volts apart. Therefore, at temperature higher than the minimal temperature of 100 Kelvin, almost all electrons from this level pass into the conduction band and become free. Below the minimum temperature of 100 Kelvin, the semiconductor practically behaves as pure one. Thus, now the number of free carriers is increased in relation to the state in a pure semiconductor. The increase is significant because all the donor atoms gave 1 free electron, which is, as we will see later, much more than Ni, intrinsic concentration. As the number of free electrons increases, the probability of their recombination also increases. Due to the more intensive recombination, the number of holes is reduced, as compared to the state that would exist in a pure semiconductor. This true also reduces the number of free electrons, but the relative reduction is far less than the reduction of the number of holes due to the much higher concentration of free electrons. That is expressed in the right where Mn and Pn are the concentration of electrons and holes respectively in the n-type semiconductor. Opposite process will take place if trivalent chemical impurities such as boron are added to the semiconductor. The figure on the right shows the situation. Boron has 3 electrons in the last shell. These 3 electrons are embedded in covalent bonds. One covalent bond, due to the lack of electrons, cannot be realized and the hole remains in that place. In that way, a fixed negative ion is created in the place of trivalent boron atom. The number of holes becomes far greater than the number of electrons. Chemical impurities that increase the number of holes are called acceptors.